I'm doing this, so sorry.
Okay.
Hello, everyone. I think we are live. Thank you for listening to us. Usually, the person that is here is Asun, but Asun asked me the favor to talk with everyone here and give the introduction because she doesn't have like a, she needs to practice more her English. So I'm here replacing her, but even though it's like a honor to me, introduce Lisa and Ahmed. Um, I think Lisa, I saw you a few times in the PSC Discord talking about a working class or something like that, and then I think I started following, and yeah, you tweet a lot of interesting stuff, and definitely when you mentioned like we were going to have you, we really liked the idea and excited us with Ahmed. So yeah, really happy to have you here. Lisa, for the ones that doesn't know, is a tech writer at Aztec, and Aztec is one of our favorite projects right now, especially because all the things that are happening with the network and Noir. I think like everyone is wanted to start with the CK development. Like Noir is super easy to start. And yeah, we haven't really talked much about Noir in 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 these talks or in the bootcamp, but I guess at some point we're going to start talking. So this is what we call CK Talks. Started after Pro Crypto bootcamp that we organized in Tegucigalpa, but then we started doing some other activities and kind of escalating now with Ahmed to Ethereum Honduras. Ethereum Tegucigalpa is a small community that started in 2018 with a goal to just give like educational content about Ethereum and similar technologies. And of course, CK is really important part for us. We have hosted a few bootcamps. So the first one you can see that's the Pro Crypto that we organized. We expected like 5 to 10 persons, and it was a full house with 25 persons. So people were standing. We have organized events about Farcaster, organized Eat Latam this year, uh, meetups. We sometimes play Dark Forest and different fun stuff. But yeah, we kind of talk about topics that excite us. And and we have few activities. The first one is there's an academia round being organized by Tegucigalpa. It's a retro. No, it's not a retro. It's a public good funding round using Macy for private voting, and the projects that can apply to this funding round is um, they need to apply with projects related to academia, like students, teachers, and anyone that has a project related to academia, they can apply. Um, also. Next week tomorrow we have a bootcamp intro to solidity. After that we are going to start a capture the flag challenge that is going to last 1 week. On the Saturday we are going to have on-chain trivia. It's more fun, so people can just reply what the question, and they were going to have some surprises. And of course the academia rounds that ends. So the capture the flag challenge starts tomorrow. It's going to last 1 to 2 weeks. And the goal is for developers that go to the bootcamp tomorrow that actually have a challenge that allows them to keep learning. We are going to be having DevCon C, DevCon talks, which is pretty much for people that like me that got rugged and couldn't go to DevCon. We are going to have a space to watch some talks and discuss them. And this is the date is pending, but I think it's going to be on 2 weeks. Yeah, these are our networks if anyone wants to follow us. And we are going to have a pop-up in the middle of the session. So yeah, keep listening to us. So if you want the pop, and I think a final announcement that I must do as a um, as I work on this round. If you attended DevCon and you haven't voted in on the funding round, you can do it. Go to devcon.org. I mean, vote.devcon.org. We are going to give a blow-up to people that vote, and we are using account extraction, so you don't have to pay any kind of gas or anything. You just have to prove that you attended that point user use SUPAS. So a bunch of technologies that we are testing. So yeah, I think that's all from my side. Lisa, yeah, I think it's better if you introduce yourself. It's you have more experience talking about it.
Yeah, so many things happening in your community. This is so fascinating. Like, wow. Yeah. My name is Lisa. I'm technical writer in Aztec. I'm fan of mathematics, and in modern blockchain, we have a lot of fun mathematics that we sometimes, I guess, use an umbrella term of programmable cryptography. So today we are going to talk about programmable cryptography. I guess, yeah, slides are live, nice. This presentation might be a bit like dense for the content because we are going to go through 4 important blockchain technologies: ZK, MPC, FHE, and TE. We are going to look at each of them, look at their like strong points and weak points, think about how the combination of these technologies can strengthen each other. And by end of the talk, we are going to arrive at the point where we understand which combination makes sense today and what we can do with that. So let's start. Yeah, some disclaimers. I don't have any serious PhD background. This presentation is based on like me reading several dozens of articles, discussing them with some people, smart people with PhDs, and doing some conclusions based on that. But feel free to argue with almost everything that something seems to you know better, or you know another perspective. Another disclaimer is that we're not comparing these technologies because they are very different and they are not really apple-to-apple comparison. We just want to understand a bit each of them and then understand what properties they can give us. And finally, this presentation was put together before DevCon. And at DevCon, I guess, the definition of programmable cryptography became wider. But we are still going to talk today about these 4 technologies. So, yeah, this is a bit about how the space looks today, because we have a bit of in crypto, we have a bit of this thing when like fight for developers, when there are like there is an abstract developer and then everyone wants every project wants the developer to use their technology, because obviously everyone's technology is the best technology. But it might be a bit confusing, especially when technologies are pretty deep tech technologies, and this is what we are having in blockchain. So let's start with the first one. The first one is zero knowledge proof. We know it in blockchain approximately from 2018, when the concept of ZK rollup was introduced. And even though in ZK rollup there is no zero knowledge proof, I guess approximately from that moment, zero knowledge proof started floating in public discourse. But briefly speaking, zero knowledge proof is a proving protocol by which one party can prove to another party that some given statement is true, or that one knows something. Like proof with given statement, it will be proof of statement. With some information, it will be proof of knowledge. But the thing is that one party can prove to another party that something is true or that they know something without conveying to the verifier, to the second party, any information beyond the mere fact that statement is true, or beyond the information that can be extracted from the proof on its own. But for the sake of privacy, we are not just interested in zero-knowledge proof, we are interested in client-side zero-knowledge proof, where by client-side we mean that whatever we want to prove should be processed, or the program should be executed on client's device, such as smartphone or a laptop browser. And by client device, we mean something that most modern humans on the earth have access to. Yeah, it should be executed client side, and the proof, this zero knowledge proof, should be generated as well on user's device client side. And this is the approach how with zero knowledge proof we can get privacy. And then like this proof can be verified and utilized by external parties. For example, in case of Aztec, as Aztec's goal is to be privacy preserving L2 on Ethereum, it works like zero knowledge proof is generated on client's device, for example, my smartphone, and then it is verified by the sequencer, and sequencer is the guy managing the mempool. And as this is zero knowledge proof, the only thing that sequencer can get from the proof is that whatever I executed client side, it was executed correctly. That's it. So this is a brief dive into how we use zero knowledge proof for the sake of privacy. Yeah. The core limitation of zero knowledge of client-side zero knowledge proof is lack of shared state. What I mean by that is that when we think about Ethereum, we have a global public state that is available. Whatever has happened on chain, it's reflected in public. But private state, it is individual for every user. So if I'm executing something on my device, my state is represented as a sum of nodes and nullifiers that reflect my personal private state, but mine and only mine. And for every user, the user knows their own private state, but nothing about states of each other. And in terms of application diversity that we can come up with and that will engage privacy, it limits us a bit in use cases. But later in this talk, we will talk about how we can combine ZK and MPC to mitigate this limitation. Yeah, the second technology is MPC, multi-party computation. It can be from two parties to theoretically arbitrary many parties. The idea is that MPC allows a set of parties to compute a joint function of their private inputs while revealing nothing but the output. Like the idea is pretty simple. There is one function. Every party provides its input privately, meaning that other parties, like party one, doesn't know anything about the input of party two, party three, party n, whatever. And the only thing that everyone is aware of is the output y. So if I'm party one, I know the function, and I know my input, and I know the output. That's it. MPC, from my point of view, is a very tricky technology because it sounds pretty simple when one explains it, like with this, oh, just a function, and parties put inputs, and then we have output. That's it. But it is very nuanced technology. Also, I think that out of all these three, MPC is the most widely used technology because it is used outside of blockchain for many years in different contexts. But okay, let's try to understand what are the nuances of MPC. So if we want to use it, what we should consider and keep in mind. First, the security model. What might happen with the security? One or more parties participating in the protocol can be malicious. For example, they can try to learn private inputs of other parties, or they might cause the result of computations to be incorrect. So while setting up the MPC protocol, we want to be sure that all private inputs stay private. Each party knows its input and nothing else. And the output was computed correctly, and each party receives its correct output. There are different levels of security for MPC, and the particular choice will depend on particular protocol. That is what I meant saying that it's very nuanced. For example, MPC security depends on how many parties are assumed to be honest. It can be less than 1/3, less than, no, not 1/3. If we say that like n is the total number of parties and t is the maximum number of malicious parties, so it can be like less than 1/3, less than 1/2, or like more than 1/2. There are even models that allow only one party to be honest, and it still will survive. Another question is how exactly they are corrupted. Parties can be corrupted before the protocol, and then they stay corrupted to the end. Parties can be corrupted at different stages of protocol execution and still stay corrupted at the end. All parties can switch between malicious and honest behavior during the protocol arbitrary amount of times. Another question is, what does it mean malicious? Malicious can mean that the parties are following the protocol as prescribed, but they try to extract some additional information, or the parties can deviate from the protocol. And while thinking about using MPC for some particular use case, one has to define kind of the security model on their own, depending on the case. Another thing with MPC is that MPC guarantees that computation process doesn't reveal any information, but it doesn't guarantee that the output doesn't reveal any information. For example, if we have an MPC function, an MPC protocol, with the function that calculates the average salary of all participants, and we have just 2 participants, and I'm one of the participants, so I know my salary, and I know the result of the computation, the average salary. From this information, I can retrieve the salary of the second participant. This is quite an edge case, but it illustrates that sometimes the information can be retrieved just like from the output. And so formally, I'm not violating anything, but I can extract the information. And finally, about MPC performance, when we think about MPC in blockchain, we should consider the following parameters, such as message complexity, computational complexity, public verifiability, and abort identifiability. Abort identifiability means the protocol was interrupted. There should be a way to see that. Public verifiability means that one is able to verify, like external party is able to verify the MPC execution. Yeah, so that was on MPC. Then we have FHE, that stands for fully homomorphic encryption. Briefly speaking, it enables encrypted data processing, so computation on encrypted data. Fully means both addition and multiplication. So if we have two encrypted messages, M1 and M2, if we sum two encrypted messages, we get an encrypted sum, and if we multiply the encrypted messages, we get an encrypted product, like in the equations below on the slide. A bit about how FHE works. Plain text is encoded into ciphertext, and like ciphertext will be our whole square thing. And ciphertext consists of encrypted data, that is yellow, and some noise, that is red, and also some noise padding and data padding, that is white. That means that when we do computations, like here, like E of M1 and E of M2, this E of M1 will look like that picture. So the computations are done not purely on data, but on data together with added noise and with padding. And with each performed operation, just by the mechanism of FHE, the noise is growing. There was like huge work on FHE of brilliant minds all over the world, and there was proposed a number of tricks how to handle this noise and make the FHE work out. One of the most widely known tricks is called bootstrapping. It's like some special operation that resets the noise to its nominal level, meaning that even though the noise is growing, we also have some trick to apply on the output that sets the noise to its nominal level. And then there was also a number of brilliant people working on making bootstrapping faster. Let's think about what are the limitations of FHE. It's a bit heavy, but we will handle it. So the first thing, if the user who encrypts the information outsources the computation to an external party, meaning that the party A encrypts M1 into EM1, but another party B, for example, makes the sum operation, sums up AM1 and EM2. So if encryption and operation are executed by different parties, they have to trust each other that the computation was done correctly. To handle it, one can utilize either zero knowledge proof or something like economic consensus, where there will be a number of parties like attesting that the operation was executed correctly. But in this case, we need custom hardware for FHE because it is computationally heavy, and it limits the number of parties who can participate in this consensus. It won't be like Ethereum, where to some extent everyone can run a node. It will be only people who possess special custom hardware can run a node. Also, in the case of the FHE blockchain, if we are thinking about blockchain network, FHE network, there is one key for the whole network. And this is a lot of memes were produced about this question, but the question is, who holds the decryption key? The most popular suggestion is to use MPC to manipulate the decryption key. Then if an external party provides encrypted input, how can one know that the party knows the input and that the input was encrypted correctly? Again, if we are using the model where one party encrypts the inputs and another party makes the computation, and I'm the party who makes the computation, and you are the party who encrypts the input, how can I know that you really know the plain text and you not just took the encrypted input from someone and gave it to me? And then if you encrypted if you encrypted the input, how can I know that you encrypted it correctly? If I'm the party who is interested in getting a correct result, there are some issues, and again, we can use your knowledge to mitigate that, but we will talk about it later. Then, while using FHE, one should ensure that the decrypted output doesn't contain any private information that should not be revealed. This is somehow similar to our example with MPC and salaries. Then thinking about like computation, FHE is heavy in terms of operations computation costs, in terms of evaluation key size, and evaluation key size are not encryption keys. It's a separate public key that is used to control the noise growth, like that. The key that we need to conduct the operation of decreasing the noise to minimum all the time. Compared to computations on plain text, the best per operation overhead we have today is polylogarithmic. Evaluation key size is huge. Even storing these keys might be a problem, not always a problem, but might be a problem. Furthermore, one needs to permanently compute on these keys because we need to settle down the noise to minimum all the time because it is growing with each operation, and all the time we need to set it down. Finally, in the case one wants to do something beyond addition and multiplication, for example, branch operation, they have to break down the operation into a sequence of additions and multiplications, always. That is also pretty expensive. So what can we do with FHE today? It's not particular blockchain case, but if implementing Shazam, like this is an application for music recognition with Zama FHE library to recognize one song out of 1,000 songs, takes 300 milliseconds. But the tricky thing about such benchmarks is that it says us pretty much nothing about how to work at scale. Like the real Shazam library is something like 40 million songs. How long will it take to recognize one song out of 40 million songs? No idea. According to Trika Brakersky, I think we can call him one of the leading FHE academicians today. When he was asked a question, can we build production level systems where FHE brings value? He says, I don't know the answer yet. And I think that this is the most accurate answer we can get today. But let's continue. Our fourth guy is TEE, Trusted Execution Environment. And if I remember correct, TEE in blockchain context was first mentioned in 2019 by Phil Dayan in the context of combining TEE and cryptography, where cryptography relies on cryptographic assumptions and TEE relies on economic assumptions. TEE is an area on the main processor of device that is separated from the system's main operating system. And it ensures that data is stored, processed, and protected in a separate environment. So it's some super isolated private sector in the processor, super secret. SGX is one of the most widely used TEEs. And the thing is that, like, to use TEE, one needs a hardware with TEE in it. So when this produced by Intel, in case of SGX, when this hardware is delivered with private key inside, public key is available for everyone. Private key is inside this hardware and never can leave it, at least by what Intel promises us. So public key is available for anyone users can encrypt messages with public key, send them to this private area. We call it also enclave, and enclave can decrypt it. It works approximately like that. We have two parts, one untrusted, one trusted. Trusted is like the super secret private area in the hardware. So there is some application that is running in trusted untrusted part. It creates an enclave. Enclave means it reserves this like super secret private area in trusted part. Application calls trusted function. Trusted function can run only in trusted part. So there is call gate. Application is running because it was called from untrusted part, but it's running in trusted part. It's running. It sees the enclave code and data. It executes something. It returns some output. And this output goes back to the untrusted part, and application is back to running in the untrusted part. That's it. So it's just like super private call to trusted part. And whatever is running in trusted part can be running only in trusted part. For TE, in context of blockchain, we really like its feature called attestations, where attestation is the process of demonstrating that the software executable has been properly instantiated on the platform. Like, for example, if we will use SGX to run a client on like Ethereum or like some rollup to generate SGX proofs, we will want this attestation that the prover is run correctly. Another feature that we also like to utilize is remote attestation, and it allows a remote party to gain confidence that the intended software is securely running within an enclave on a fully packed. Limitations of TEs that we discussed is side channel attack, meaning that if one observes a program's indirect effects on the system during execution, it might leak some information if an application's runtime behavior is correlated with the secret input content that it operates on. And another thing is that using SGX, one trusts Intel that everything is fine and the hardware is delivered already with a private key inside the trusted enclave. Finally, as a large enterprise, Intel is pretty slow in terms of new attacks patching. And also, as SGX is a pretty new technology, we don't know all types of attacks that might happen and will happen. This is also like this statement is fair regarding pretty much all technologies we are discussing because they are all pretty new. Like following the general blockchain discourse about TE, I feel like the most common opinion is that it's not the question if TEs will be exploited, it's the question when they will be exploited. But nevertheless, another thing is that with SGX, developers depend on specific hardware produced by Intel, and one day it might be just economically unreasonable for them to continue producing this hardware or continue maintaining this hardware. So they just might deprecate some specific unit, specific item, or change something significantly for some version, and applications might become incompatible or even like break. That was the case in 2021 when SGX was deprecated on consumer CPUs. And finally, when something is running privately in a private domain, it's hard to detect fast that something is wrong. So now the question is, should we just combine all of these technologies and make a super powerful programmable crypto creature? My answer is approximately in this picture, saying that however we combine them, we still need ZK for verifiability. because the initial reason why we even started dealing with programmable cryptography in blockchain was this property of verifiability. And whatever we use, we want to still have this property of verifiability. Another important thing is that even if each protocol or each primitive on its own seems not very complicated, and we can see examples of it being implemented, when we start combining them, it often leads to huge overhead. Because combining two very complex technologies is not an easy task, and combining 4 technologies, it's insanity. But let's think about it. A very widely popular thing today called snarks, or collaborative snarks, that in particular means ZK, combining ZK and MPC, meaning that several parties jointly generate a proof over their secrets, mutually distrusting parties, and get publicly auditable MPC. Publicly auditable means verifiable. There is also the thing as delegated ZK snarks that works a bit differently from co-snarks, but it's still similar. And the core reason we can use ZK MPC is for shared private state on a private rollup, on a ZK privacy preserving ZK rollup like Aztec. And for example, one of the teams working on ZK MPC and collaborative co-snarks is Tasio. And it seems that we are going to have it pretty soon in a production level state. ZK MPC is not really simple. It's a very, very sophisticated thing. To give you like a glimpse into why it is not simple, assume we were doing ZK MPC like straightforwardly. Just we have elliptic curve operation if we are doing like elliptic curve based snarks. So we can just decompose the elliptic curve operation into like base field operation, and then just perform them in MPC, like addition multiplication. But in this case, for like one elliptic curve operation, we will get like tens of field operations and scalar products. It will be huge. It will be huge. It is doable theoretically. If we are going to use it in practical aspect in blockchain, it's huge overhead. It doesn't make any sense. So the suggested trick for the MPC is that MPC is applied not to like field operations, base field operations, but directly to elliptic curves operations. And this, like the secrets, the inputs that each party will provide, it will be elliptic curve points. Yeah, without going too much into details, just to provide some intuition why it's not like, oh, we will just put together the MPC in like the most straightforward way and it works. No, we will put the MPC, but in a very sophisticated way. Then MPC FHE to tackle the issue who holds the decryption key. So yeah, we can, for like FHE network, we can distribute decryption key to a number of parties. Still have a problem of, and other problems, especially with like verifiability. For FHE, we wanted a proof of correct input encryption and proof of correct computation. Can we do it today? According to some benchmarks that Zama published, proof of one correct bootstrapping operation, and if you remember from the beginning, bootstrapping operation is when we settle down the noise after one like addition or multiplication operation. So one bootstrapping operation can be zero knowledge proof for one bootstrapping operation can be generated in like 21 minutes. And we need to generate these proofs like for each operation. So it seems that, again, for practical reason, today it is not feasible to use it in blockchain in production. Talking about, like, if one think about using FHE as like the main privacy technology, it won't be FHE, it will be ZK MPC FHE if we want to have a decent level of security and verifiability. How can we know for sure that the encrypted piece of information got from a specific party was encrypted exactly by this party? What if party A took a piece of information encrypted by party B? Again, we can use zero knowledge to mitigate this. So we already apply zero knowledge in several places of MPC FHE hybrid. Whatever, the MPC FHE is a very heavy creature. We can construct it theoretically, but theoretically. So some conclusions of this talk. We will start our conclusions from this side. TEs seem to be good. Independently of number of jokes and memes done on TEs, they seem to be really our friend if we use them with other technologies. So whatever we can run in TE makes sense. For example, one of the things is to use TE for multi-proof or for a rollup. So if you have a ZK rollup and it is running like 3 zero knowledge proof systems or just snark generating provers and 2 TE provers on different clients. And then it has the rule that the proof is considered valid if 3 out of 5 proofs were delivered. It will be that we always have 1 zero knowledge proof and 2 TE proofs. These 2 TE proofs provide us additional security, but in terms of the cost, we still pay and wait just for 1 zero knowledge proof. So they kind of like strengthen the security for free. One should not use TEs for storing secrets. It is execution environment. To construct ZK proofs or participate in MPC protocol, it's not a separate thing. The secrets can stay in ZK proof or MPC protocol while it's actively computing, but then they are discarded. Trusting TE for 30 seconds is probably fine. Trusting TE for a month is probably bad. This is, of course, not an axiom or objective opinion, but I feel that it's pretty much the consensus in the industry right now. And just from like this picture, one can see that without TEs, the attack vector is wider than with TEs, even though with TEs, the attack vector is not 0. But it's much better. And TE proofs are almost free in terms of time and cost. So just seems TE is really our friend. Yeah, and MPC is our friend as well. And it's not because we are really very friendly, but because we really like how MPC can be utilized to encrypt and decrypt shared state, and because today's state of ZK MPC is good enough to be used. So we can put all our 3 technologies into this table and get the idea that with client-side zero knowledge proof, it seems to be the most robust and flexible and secure approach, because whatever we do else, we have to to add ZK to it anyway to get verifiability. But to have shared state, we need this ZK MPC, so it's not purely ZKP, client-side ZKP, ZKP plus MPC. So we have 2 finalists, either ZK MPC or ZK MPC FHE. My perspective on it is the following. We definitely should explore both. Theoretically, not theoretically, like academically. If we are doing research, we should explore both. If we are thinking about something on production level that we can do today, we should go with ZK MPC or MPC ZK, MPC ZKP, however we call it, because this is something that we can do today. So if we want to build on blockchain and we need some privacy that will be flexible to build wide variety of application, we should go today with ZK MPC. In 10 years, might change a lot. But for our industry like blockchain, it's even not 10 years, it's like maybe even 5 years if we check. The tech stack is drastically different from what we have 5 years ago. Yeah, and that's pretty much it. And yeah, whatever we do, ZK or ZK MPC or ZK MPC FHE, it can run in TE just because it's almost free and it adds some additional security. And that's pretty much it. I don't remember what this QR code says, but you can check. It's probably some article. Yeah, and if you have any questions, you are welcome to ask or message me anytime with any questions. Very smart, very simple, very funny, very boring, whatever.
Yeah, that was super great, Lisa. Yeah,
I love the memes.
yeah.
The memes were super good.
I did my
Yeah.
best. I did my best for memes.
Yeah, also it provides like a good overview on where we're at, and yeah, maybe we have heard about many like many of these technologies, but just learning how they combine, I think is super interesting. Yeah, actually, I have some questions, some things that yeah, so some questions that I have like, but maybe we can start with a question from the audience if there are. Also, everyone remember to feel free to ask a question and we can read them now. Okay, so the first one from Oscar is, how can trustless system ensure correctness of outsourced computation in FHE without relying on centralized or proprietary hardware? I think you kind of answered that already, but yeah, go ahead, Lisa.
Yeah, the only way to do it in a kind of trustless manner is to use zero knowledge proof for that. So if you want like really trustless FHE, we will need to use ZK for correct input encryption, and we will need ZK to use
So while Lisa connects, I think it's a perfect moment to share the POAP. So let me see if I can share it right now.
I thought it was me.
Yeah,
who
no.
got disconnected.
Yeah, it was Lisa. So yeah, just go to the POAP website or your POAP app and go to Mint POAP, select or type in the secret word, which is CK Talks and the number 3, all in. You don't have to use caps, just small. Yeah, the keyword is going to be open for around 40 minutes, maybe less. So I will say that. if you have time. Now it's the best.
Kristen, can you
moment.
put the other screen in big? Thank you.
Yeah, sorry. I think Lisa's back.
Yeah, I'm incredibly sorry.
No worries. We were just in time to share the pop, so we were in good time. Let me just remove you. Okay.
Yeah, we were talking
about you were saying that ZK is the way that we can ensure like the computation is correct.
Yeah, but it's like it's as I described there. Like for example, if we will apply ZK to prove the computation correct execution, like in the example was that like one ZK proof of one bootstrapping operation today takes like 21 minutes, and I think it is doable. Like in terms of math, it is doable. But when we will arrive at this point when we can do ZK proofs of like really FHE, it might take 5 years, it might take 8, 10, I don't know, and no one knows.
Yeah, and speaking about that, I just realized by seeing your presentation, I just realized that I was maybe too bullish, maybe on on all this technology, because I just like took it like as a fact that this is going to scale, but I never been like in the trenches of the mathematicians writing all the papers and optimizations. Yeah, I've never been like in that front. I don't know where that is. But the thing that I do know is that so for example, I remember seeing a video from Nick Szabo saying that CK may never be possible in the foreseeable future, and now they are. I've seen, for example, the first, I saw a podcast with the CKH team that's saying that the first CK proof in their protocol demo from sending from wallet A to wallet B, making a CK proof of that took about like 1 day. and now, just a few years later, here we are. We have CK EVMs, we have like CK protocols actually working. So I was wondering, like, what about you, Lisa? What is your take? That like, what is your like? Basically, yeah, it's like a bet at this point. Like, where would you place your bet? That do you think like it's going to happen like faster than we think, or do you think just having CK proof of FHE is going to take like a long time?
I don't know, but I think it's very proportional to the number of people working on that. It also like depends on like ZK. We want like ZK FHE for consumer hardware, or we want ZK FHE for custom hardware. These are also like two absolutely different things. Then also like, but it's also like not that straightforward with like client side zero knowledge proofs. We know how to do it very efficiently today for elliptic curve based snarks. If tomorrow we want to snarks, still to do, and I don't know when we have efficient client side proof for hash based snarks. But all these technologies, I feel, depend drastically on how many people work on them. Because the more cryptographers think about it, the faster we get the result. But it seems to be doable all. It's not like no impossible. No, it seems, from what I know, there is no miracle required for any of them. Just a huge chunk of optimizations and smart tricks.
Cool. Yeah. By the way, there's something that I've been thinking for for some time that I think it sounds like a fun future to have, is having like CK devices, CK like client proving devices. I think that would be super cool, just to advance. Yeah, yes, just to advance yeah, to having being able to have like client side computation, yeah, just better. And yeah, you can, I think you can advance in many fronts in the cryptography protocols. The hardware can have like some advancement too. We can maybe find good ASICs that are easy to produce. Yeah, I don't know. I think, yeah, I agree with you. Like, and yeah, hopefully like more people get interested in this, and I think people will, because there is a lot of opportunities also. And yeah, I think that's going to be super fun. Um, yeah, also I have a couple of questions about, yeah, you mentioned a decryption key for FHE, and like what is the role of the decryption key? Like, actually, what is it like? Will you be able to see all past history message, like, and decrypt them, and be able to reveal them? And yeah, how does it work, like the decryption key?
Yeah, for example, you want to use FHE to have private DEX or something like that. So you need some mechanism to, like, the DEX, the current state of the DEX should be somehow available for people to do their trades. So for example, even the state of, like, if I want to do one trade, I need the state of like particular liquidity pools. So I need to, even if like the overall DEX computation is made like on encryption data, then I need to know the current state. So this current state of a network or of a DEX or whatever we want to use FHE for privacy should be decrypted. So there should be some key. So the worst case scenario, we have a network, and this network holds one key and decrypts the state. To mitigate it, we can have like MPC committee with number of parties.
I see. So basically, yeah, it can be like, yeah, worst case scenario, it can be like one decryption key to decrypt all the protocol, and yeah, best case scenario, we can share it with MPC into multiple parties. And I guess that best,
Yeah.
like super best case scenario will be like every participant of the protocol holds a fraction of the, like, whole a specific access to the private key. So basically, you can decentralize the decryption. Am I getting it correctly?
I think it would be problematic, except for with fixed number of participants, because in general, the idea of blockchain that whoever wants joins, whoever wants leave.
Yeah.
So it's some fixed committee.
Yeah. I guess that if you
know,
opening it too much,
MPC.
yes, I guess that if you, sorry, I think you're cutting a little bit, but maybe if you opening it too much, it will just stop becoming like permissionless, like, because you will have to hold part of the key to be able to join, and you want, if you're, as you say, like, if you're in blockchain, you want many people to be able to join. Yeah, that makes sense. Yeah, other like thing that you mentioned that I have heard a lot about it, but I'm not sure what it is collaborative snarks. Like, yeah, can you please define like what it is? Like, explain what those are?
Yeah, in like regular snark, you have one prover generates the proof. So if it's not client side, you are a prover, the user, I give you the witness. I give you the witness, like my secret, so generate the proof. In collaborative snark, it will be kind of like of proof who collaboratively generate the snark. So if I'm the user, I split my witness between a number of provers so that none of them knows the witness entirely, and everyone has just a fragment of witness, so they can generate the proof without any of them knowing my whole witness. I think the project that is currently utilizing it is WorldCoin. This is exactly what they do for storing Iris codes and generating proofs on Iris code. They split them into several parts and then generate proofs where like every part, every prover in like this collaboration has only part of the Iris code.
Okay, so but in order, like in order for in terms of liveness, do you need to all the parties to submit the proof in order to verify, correct?
They collaboratively generate only one proof. Snarks, in terms of like performance, seems to be very similar to one prover generating the proof.
Okay.
Elliptic curve based snarks. This is important.
You mean performance in terms of verification, or
how much time? No, how much time it takes the prover to generate the proof, how large is the proof, how much time it takes to verify the proof.
Oh, really? So even if it's like if everyone is generated like by their own, even with that said, like is it like not like that harder to generate, like yeah, in terms of like comparing it, if there's only one, there's not a lot of overhead basically by making a collaborative. That's interesting.
Yeah, but this is the thing that they are not generating everyone their own proof. They're collaboratively generating one proof. This is like the trick. Like every participant adds a bit, we can say like that, to the proof.
Okay, I see. Yeah, I think I was getting confused, but it's not the same as aggregation or recursiveness, right? This is something different, right?
Yeah.
I see. That's interesting. And yeah, and also like I have two more questions. Like first one is like how do you see the current landscape of ZK? It's something like is evolving, is something that is a lot of things going on. Do you think it's a little bit more calm down, or is there like a lot of new things coming, do you think?
Yeah, and evolving insanely.
Insanely, yeah. Good adjective.
Yeah, a lot of things. We like in blockchain, we mostly like about elliptic curve based snarks or hash based snarks, but there are also like ideas to make lattice based snarks, and I know some people are exploring snarks beyond elliptic curve snarks and hash based snarks. In these two things, like also a lot of improvements for optimization, for efficiency, everything only like on folding stage, like folding schemes continue to arrive every 2 months, every 3 months. We are at a very interesting point when we kind of have ZK snarks good enough to do things in production, but it's definitely not the best thing we can have. So there are people who are just happily building with what we have, but there are also a bunch of people who continue pushing this forward. And honestly, like from my personal view, I think that like in what we will have in 10 years and what we will call ZK snarks, ZK proofs, it will be like super different from what we have today. I think so.
Yeah, and it's been like that for a while, right? And
Yeah.
happy to see like people like that are very deep into the ecosystem. Yeah, just thinking about, because I think that's a general uh, consensus of people that are like into CK, that thinking that there is a lot more to come. uh yeah, and just the last question, in general, like in terms of all these combinations, combining FHE and MPC, CK, like what are the ones that most, maybe something that caught your attention? What are you looking forward to, like maybe use cases, or maybe technologies that you have seen that being developed right now? Like what are the ones that excite you the most? Like what are the ones that you're looking forward to see?
Of course, it is client-side proof generation with MPC for shared private state. So like client-side proof generation is what we are working on in Aztec. Like this co-snark thing, combining ZK and MPC that we can utilize for Aztec for shared private state. This is something Taseo is working on. I am very, very, very excited to see how it combines in production and what applications we will have with that. Because in terms of performance we can have, it's enough for what we do in blockchain today. It's enough, and we will be able to have this what I call explicit privacy, where pretty much whatever can come up, the developer can come up and it needs privacy, can be built with this. So I'm very excited.
Yeah, sounds very exciting, and sounds like something that the use cases that will come from that are something that we're not imagining just yet. Some very, very new and very cool stuff. Yeah. I don't know, Chris, if you want to add something.
Yeah, I definitely love the presentation. Like Ahmed says, it opened my eyes. Like on the Macy Discord, sometimes we get people like, "Hey, we have this issue with trusted coordination, right? Like he's the one that can decrypt all the posts and publish it." So every time like someone watch a talk about FHE, they come to the Discord and say, "Hey, you can use FHE to kill the coordinator, right?" And I always thought like it's a good idea. Even I myself thought about it sometimes, but I never realized like we're still super far from it. And you talk up with that. Also, yeah, really love what Aztec is building. Like even now that beam chain was announced, and that we want to snarkify that we. I think most people doesn't realize that snarkifying. I'm pretty sure like it's not including anything about privacy. It's just like
No.
proofs, right? Yeah. So it's like the same state, and Aztec is building something that at least I still can't just how it works, but it sounds super interesting. But yeah, thank you for your talk. It was super good.
Thank you for having me. It was a pleasure.
Thank you. Yeah, it was super great. And yeah, thanks everyone that is either like seeing this live or seeing it like just like after that. It's going to be posted on YouTube and also Twitter, I think, right?
Yeah, right now it's on Twitter and on YouTube. So the recording after we end this is going to keep there. So yeah, thank you, Lisa, for your time. We don't want to steal you more. I know we can keep talking about CK for hours. So yeah.